So this time, let's look at a different type of structure. This is a cantilevered structure. A cantilever is a structure that's supported only at one end. It's a fixed support and free to move at the other end. So this thing, when it is loaded, it's going to come out and deflect down like that. That's a cantilever. In this case, it's not free to move up or down on this end, not free to move back and forth, and not free to rotate. Okay? So the first thing we need to do in this case is we need to draw the free body diagram of the cantilever showing the reactions instead of the support. So below here we have the free body diagram. Again, a free body diagram shows all external forces and all geometry on the structure. So because we're not able to move vertically, we get a vertical reaction, call it RV. We're not able to move horizontally, so we get a horizontal reaction, call it RH. And we're not allowed to rotate at this end, so we get a moment reaction, call it RM. Okay, so that's a moment. So this one will have units of pound-feet. And now we just proceed the same way as we would proceed with the other beams. We use our three equations of equilibrium. Sum of the forces in the x direction equals 0, sum of the forces in the y direction equals 0, and the sum of the moments equals 0. Now the nice thing about this is, because we only have one vertical and one horizontal, it doesn't matter which way we solve these problems. And this will actually turn out relatively easy here. So let's just do it. Sum of the forces in the x direction equals 0 equals RH. RH equals 0 because we have no applied loads horizontally. Let's jump right to let's go do the sum of the forces in the y direction equals 0. Equals RV going up minus 300 pounds going down. That has to equal 0. So we can conclude from this that RV is equal to 300 pounds. This third equation is one that we haven't dealt with a concentrated moment like this yet, and this is sometimes difficult for students to grapple with because we don't multiply that by a distance. We just use it as it is. A lot of times I like to call this just M. Okay, that might make it easier to understand. So let's just call this one M. That way we're not confused. And we'll call it M at point A. Okay, so if we sum the moments about point A, this way being positive, we get this unknown MA. And of course we've assumed that it's going counterclockwise, so it's positive. And then we get 300 pounds times 12 feet about point A. It's spinning this way, which would be negative, and of course that has to equal 0. Oops, that's negative. So we get directly MA is equal to 3,600 pound-feet. Okay, and we're done. So solving the cantilevers is actually simpler because we don't have two vertical reactions. Now let's take this one step further. Let's take the same thing and say, okay, let's take into account the self-weight of the beam. So let's draw a new free body diagram here, and this time let's include a uniform load that represents the self-weight of the beam. And let's say this beam weighs 20 pounds per foot. Okay? So the first thing we need to do is get that 20 pounds per foot into a resultant so that it's easier to to grapple with. So let's do that. So the resultant of the 20 pounds per foot would be concentrated at its center. It would be 20 pounds per foot times 12 feet is equal to 240 pounds, and that would occur 6 feet from the left end. Okay? So basically what we've done is we've taken that uniform load, concentrated it all at the center, 6 feet from the left. And now we can go ahead and just solve our equations. Sum of the forces in the x equals 0. Sum of the forces in the y direction equals 0. And the sum of our moments equals 0. Once again, sum of the forces in the x direction equals 0 equals RH. So RH is equal to 0. This time, sum of the forces in the y direction, we have an additional 240 pounds. So we get RV going up minus 240 pounds minus 300 pounds, and RV is equal to 540 pounds. Okay, now let's look at our sum of our moments. Again, let's look at the left end of the beam, and we get sum of the moments about point A equals 0, this way being positive. We get the moment, m, and again, we don't multiply that by any distance. M is m. Even if I was looking at the moment of that about this end of the beam, it would still just be m. M already has units of pound feet, so we don't add anything to it. Again, it's positive. We get the 240 pounds. That's 1440 pound-feet plus 3600 pound-feet, where m is equal to 5040 pound-feet. RV is 540. So that tells me is that we have to have a concentrated twist or a concentrated moment of 5040 pound-feet at point A to keep this cantilevered beam from moving. The procedure was identical to the one we did up here, only in this case we had this additional value in this equation and in this equation. And it increased the moment at the support considerably from 3600 to 5000.